Jen, you didn't look at the homework there?
Yeah.
Is it easy?
No,
difficult?
it's hard. It's hard,
It's
yeah.
hard, right? So I was thinking, let's make it due on Wednesday.
Thank you.
Right, Wednesday next week.
Wait, do we have another homework that's then due on Friday? Or?
Another homework. The thing is, because I want to have the homework weekly, right? The idea is that we do one chapter per week, and if we actually follow that timetable, we'll finish the whole book. And then homework number 4, right? So homework number 4 due next Wednesday, and then homework number 5 supposedly due Friday, right?
So try.
That's longer.
Everything. No, this was supposed to be due Monday, right? I changed it to Wednesday. The reason being, there will be a discussion session Tuesday. What you do, we can talk about this homework, right? And then there is another discussion Wednesday 4 to 7, and we can talk about that homework.
So finish the first one this weekend.
Is that
Second one.
deal?
That makes sense.
Yeah, that's fine.
And then I will announce homework number 5. I didn't have time last night. I'm going to announce it tonight. And let's see, one more announcement. I should get going. That's also, I was just thinking about the midterm. Just to make things simple, maybe for the final, I'll just make it comprehensive ENM only. So we done with that more part. Since you work on the midterm for like it's almost 3 hours for the midterm, so I thought well we finish that part of the class. So next time you have to deal with it will be physics 112. Okay, so final is comprehensive. Comprehensive ENM, right? But of course, with emphasis on chapter 5 to 10, right? Because the second midterm, number 2, will be on chapter 1 to 4. Okay. Questions so far? Everything's clear? Okay. Let's continue with the discussion on electric potential. So just to review, recall that potential is given as an integral with a minus sign, the indefinite integral from some reference point R S. Okay. And so the particular VR minus VR naught is equal to minus from R naught to R S. Okay. Now for a finite, for a Judge distribution of finite extension, right? So if I have some finite extension of charges here, rho, right? Then you can assume that it's best to use your reference at infinity instead of the potential at infinity to 0. Then you're left with the potential at R will be equal to minus path integral from infinity to R e dx, right? Okay. But this is not always true. You don't want to use. Sometimes you don't want to use this if your just distribution is of infinite extent, right? You want to use a different reference point. It's better to use a different reference point. In particular, for the purpose of the next half an hour, I want to look into a potential coming from an infinite slab, right? Of just an infinity, right? direction, this is y, okay? And as you know from Gauss's law, or from Gauss' law, the electric field is given by this normal, right? The electric field is the same everywhere. It's pointing away from the sheet. If sigma is positive, by the way, right? A lot of this discussion assume implicitly that the charge is positive, and if it's negative, everything pointing the other direction. And then the electric field is given by sigma over 2 epsilon, right? Okay? So I want to calculate potential everywhere in this case. Okay? Now, here, it's probably not wise to use your reference point to be at infinity. You can, right? But it doesn't work very well. It's not very illuminating, right? It's probably best to just use point somewhere finite with respect to the sheet. And I'm going to choose just exactly the same for this here, okay? So let's look at the portion over here where C is positive. Okay. Then the potential at Z minus the potential at 0 is equal to minus integral from 0 to C E. Right? I'm just going along a straight line here. That's my path. Okay? And since this is only constant, then what I have here is just minus sigma over 2 epsilon naught C from 0 to C, right? So, and then as usual, I can set the reference to whatever value I want. And let's set the potential at 0 to be equal to 0. Then I'm left with the potential at C to be equal to minus sigma over 2 epsilon naught C. Okay? How about at, this is a bit tricky, but in the end you can do it however you want to C less than 0, right? Anything to the left of the sheet. Let me consider a pathway going like that. Just so that I can easily take care of all the minus sign, right? So then in this case here, the potential at 0 minus the potential at C. Okay, I'm moving myself from, say, minus C here all the way to 0. So in this case it's minus C. Okay, and it's equal to minus an integral from minus C along that straight path all the way to 0, E, C. Right? Okay. But E is pointing, the electric field is pointing in the negative direction. Just bear with me. There's a reason I want to do it this way. You can do it the other way too if you want. I just want to take care of the minus sign more transparently. Okay, so this becomes, the dot product is negative because the electric field points in that direction and DC point in this direction, right? That's the reason I'm using this convention. Right? I'm taking the curve to go from minus direction all the way to 0. So this becomes the minus cancel. This becomes an integral from minus C to 0 sigma over 2 epsilon naught dc, right? And this just becomes C 2 epsilon naught minus C to 0. And this is just minus sigma C over 2 epsilon naught, right? Actually plus, no? Is that right? This is just equal to 0 minus sigma minus C, right? Over 2 epsilon naught. You'll have it sigma C over 2 epsilon naught, right? And again, just to be consistent with for the whole problem, the voltage at 0 is you set to 0, right? Then you have a V minus E will be equal to minus sigma C over 2 epsilon naught. Okay, is this clear so far? So if I draw the graph the dependence of the potential on R or on Z, I have something like this. This is equal to 0. Right? Then the potential is linear. Okay, and has a kink here at 0. And this has a slope of minus sigma over 2 epsilon naught. And this has a slope of sigma over 2 epsilon. Okay? Okay? And if I just draw it on this space here, this is your slab, this is the electric field. Right? Everybody electric field is like that. It's constant everywhere. Right? I can draw everything with a constant C has the same potential. Right? Okay. This straight line, this is your slab. This is your thin slab. Okay? And these are lines of constant potential. Okay, so this line here is Pz naught equals Z naught, then it becomes just minus sigma Z naught over 2 epsilon naught. Okay. Any questions so far? Is this clear? So this is one example. We actually will do a lot of examples relating to this problem here in chapter 3 when we discuss inductors and capacitors. For now, I'm going to leave it and talk about another problem.
Question?
Yes.
Why is it negative on that side?
In which side?
On the V negative Z equals to the left. Just the final result.
Here. Oh, because
Here's,
this is the indefinite integral, right? With the limit of integration of 0 and minus Z. So I guess in theory I should call this Z prime, right? So this is the indefinite integral from the limit of minus Z to 0.
No, I mean the answer.
Because here there is a minus sign from here.
Oh, okay.
Yeah. V naught minus V.
Oh, so this was just calculating V negative Z.
Yeah, V
okay,
negative
yeah.
Z, right? Yes.
Got it. Yeah.
So yeah, this is equal to that. So this becomes minus sigma Z over 2 epsilon naught. Okay. I hope I didn't make a mistake because I kind of know where I'm going. I kind of know that this is the answer I want. So maybe I make a
No,
mistake.
it's fine. I just
I don't
didn't
think
see
so.
that part.
I think I did it correctly.
How come in this case we define the potential as 0 to be 0? Like before, didn't you define it at infinity
Yes.
to be 0?
Right. For a charge distribution of finite extension, it's possible, in fact, it's preferable to actually put the reference point at infinity, right? Because if things are of finite extent, then the electric field at infinity, everything diminishes to 0 at infinity, then you can set, okay, that's my reference point, right? My at infinity. But say in this case here, right? For example, this case, right? In the case of the infinite slab, right? The charge density goes all the way from minus infinity to infinity. That is an infinite slab, right? So, I mean, just looking at the result, right? As you see, the potential goes to infinity.
Oh.
Right? At infinity. It's difficult to set your reference. In fact, you can if you want. You can set the reference at whatever value you want at infinity. But it's less well defined. It's a lot easier to set your reference at 0 in this problem. Right? Similarly, this is a diversion. Remember, if I have an infinite line charge of charge density lambda, right? We did this at the end of class on Wednesday. We find that it's best to use some reference point somewhere R naught, right? Finite distance away from the line charge, right? And we find that PR is just minus lambda over 2 pi epsilon naught log R plus constant. Right? In fact, here you cannot set this to be 0 at infinity. It's difficult. Also, you cannot set it at 0 because it's also difficult because here the field goes to infinity, right? So you just have to choose your reference somewhere else. Okay. What matters in the end is always a voltage difference, potential difference. So it doesn't matter really where you put your reference. Okay, let's move on. Let's move on to a more difficult subject. Actually, a more difficult example. I want to keep that. Dipoles. Dipoles is a case where you have a finite charge distribution. Okay, so if I've consider this, if I have two charges, plus Q and minus Q, okay, separated by distance L, okay, and suppose L is actually very small, right, and I want to look at the field everywhere, I want to look at the field everywhere far away, okay. This is extremely useful. You'll encounter the dipoles a lot. In fact, in chemistry, say water molecule, right? Water is a water molecule, right? So it's a dipole. Okay, this is your oxygen. This is your hydrogen. I'm just drawing a caricature here because this is electronegative. So pull the electron this way. So this becomes minus, the hydrogen becomes positive. So there is a charge separation here, right? So in this case, you have a dipole pointing in that direction. Here, you have a dipole pointing in this direction. Okay, and you learn again. This is to motivate you. You learn this later on. Maybe we actually discuss this a little bit in chapter 10. Right? Most atomic transition, right? Most atomic molecular transition, when you have things emitting light, right? Usually this is a dipole transition, the dipole radiation, meaning that what you have is a dipole that oscillates, right? And as it oscillates, it actually emits light. Most transition are dipole transition, okay? Oscillating. Since we're in Berkeley, there is a famous experiment here done, for the longest time until late 5-10 years ago, on the electron dipole. So you always think of an electron as a point charge, right? Good. Certain theory of physics allow the fact that the electron might have structure. If it has structure, then maybe if you actually, it's separated, so maybe it actually contain a dipole, right? So in this case here, this is a charge of electron, this is a charge of electron, say, right? It's a Q, right? And then people want to find what is L, right? And famous experiment done here with a limit on L to be less than 10 to the minus 28 centimeters. So this is the limit, and in the end, I don't know what's allowed by theory and what's not allowed by theory, but this is the limit of an experiment. That if electron contain a dipole, then the separation between those two charges are very small. Okay? So that's the motivation. And here we want to find the potential and the electric field for a dipole everywhere. Right? It's a good example of a charge distribution of finite extension. Okay? So let's draw that again. Plus Q minus q. Let me put the origin over here in the middle. Okay, this is origin, this is x, and this is z as usual. Right? And I want to look at the field somewhere over here, R. Okay? So let's call this R1, and let's call that R2. Right? Okay? And R here is much, much larger than L. Okay? What is the potential? The potential at R is given by, again, we did this last time, right? If it's a finite charge extension, then I can safely find the potential to be equal to 1 over 4 pi epsilon naught, and integral over some volume, d prime, rho r prime, d prime, over r minus r prime, right? Okay. Just take any differential volume, right? And the potential due to the differential volume goes as 1 over r, right? So in this case, I only have two charges. It becomes very simple. It becomes 1 over 4 pi epsilon naught, okay, q over r1, right, plus minus q over r2. Okay? Is that clear? It's as simple as that, right? So the rest is just math. You just find the answer that is physically meaningful. Okay? Now, if R is much greater than L, it's safe to actually, instead of drawing it this way, because R, consider this point to be at infinity, right? And I'm going to draw, sorry to erase this. Yeah. I'm going to draw R1 and R2 to be just parallel to R. Okay. And this is actually find the two. The difference is going to be much smaller in the order of delta R, or in the order of L. Okay? So in that case, if this is theta, right, I can draw a line perpendicular to these three lines. Okay? Then in this case here, this line here, you can convince yourself, this is L over 2. This is also L over 2, right? Then this line, if that's theta, then this is also theta. Then this line becomes L over 2 cosine theta. And also this line here is also L over 2 cosine theta. Okay? Then R1 becomes just R minus L over 2 cosine theta. Okay? And R2 is just R plus L over 2 cosine theta. Okay? Is that clear so far? If it's not, read through the book, I'm following the convention completely. And since L is much, much smaller than R, right? Remember, I can use this approximation, right? 1 plus x to the power of n. But let's just be specific here, right? 1 plus x to the power of n is approximately 1 plus nx, right? Okay? So what I have look at that equation. Q of R is equal to 1 over Q over 4 pi epsilon naught. Okay? 1 over R1 minus 1 over R2. Okay? This part becomes 1 over R minus L over 2 cosine theta. minus 1 over r plus L over 2 cosine theta. Right? So let me write r outside, 1 over r 1 minus 2r. Okay, this is clear so far, this step? Okay, so now I can make the approximation, make this small x approximation of that polynomial expansion, right? Because this component gives much more than 1, right? So I'm left with q over 4 pi epsilon naught, 1 over r, right? This becomes 1 plus L over 2r cosine theta, right? Because 1 over 1 plus x is approximately 1 minus x, right? Is this too detailed for you? Shall I just give you the answer? Or
I think this is good.
Okay.
Yeah,
Okay.
keep going.
I'm just wondering. Okay. And then here, this is minus, again, 1 minus, because this is 1 over 1 plus x, so it becomes 1 minus x. So this becomes 1 minus L over 2r cosine theta. Right? The 1 cancel. Okay? So you're left with q over 4 pi epsilon naught. Okay? 1 over r squared L cosine theta. Right? Half and half become 1. Okay? That's your potential. Is this clear so far? Right? So, let's define a dipole moment. To be equal to P, right? It's usually called P. To be equal to Q times L, right? So usually it's just the charge on just one of the charge times the separation between the charges, right? And the potential at R coming from a dipole then becomes just P cosine theta over 4 pi epsilon naught r squared. That's your potential everywhere. I guess everywhere far away, right? Everywhere far away. Where R is much, much bigger than that. Okay? Notice that for a monopole, right? So it's just plus Q, right? If I have plus Q, then potential goes as 1 over 4 pi epsilon naught Q over R. Right? So it has a 1 over R dependence. Right? But for a dipole, it actually looks sharper. It has a 1 over R squared dependence. Okay? And this intuitively makes some sense because what happened here, because of the plus minus, what's that? Plus Q minus Q separated by L. These two charges almost cancel one another, right? So you're left with the residual, right? Because the fact that they're not on top of one another, you have a residual field, right? And the residual goes down as 1 over R squared, right? For a monopole, this is 1, this is 1 over R. Okay? So far so good.
Question, what's this P?
P is a definition of a dipole moment. P is just Q.
Just something we define, right? So
But yeah, define that, right? Give it a new name, right? This is this configuration, I call it a dipole, right? And has a moment, right? And the moment is just the charge times the separation, right? And because this is just Or you can write it, if you want, you can write it as QL. Okay? Okay? Don't be fancy, maybe. Question? Okay, we'll come back to this soon.
You said that we thought that the electron, we were thinking that
yes,
it might have a dipole.
Yes, huh?
Why would we think that if from far distances it doesn't follow one of our squared?
No, because it's very small. What happens is the P becomes very small, right? So meaning that, yeah, there is monopole, right? So you're right, it's a very good question. Meaning that total charge is not zero. In this case, the total charge is zero, right? So this is a caricature, by the way. This is an electron, right? It has a charge E, right? So maybe on top of this electron, actually it has a structure, right? Plus Q minus Q, right? So the monopole part, of course, gives you 1 over r squared, gives you potential 1 over r. It's a very good question. Sorry, I overlooked that, right? But suppose electron contain more structure than just a monopole, right? And because who knows, right? We just want to push the limit of like, okay, well, is it really truly a point charge? What if it's not a point charge, right? What if it has some structure? Right? Yeah, sure. So there is a monopole portion of it. But suppose the distribution is not uniform, say. Right? If the distribution is not uniform, then the next order is your dipole. Right? Say if there is more charges here, less over here, right? Then suddenly you create a dipole. Right? And then the experiment was done to limit how big the dipole was. Right? So it's a very beautiful experiment, very intricate, and it's.
So in the case of the one that you drew, just plus Q minus Q, do they have the same amount of charge?
Yeah, it's plus Q on one side, it's minus Q on the other side.
So there is no dipole?
Right? Sorry?
So there is no dipole, or there?
No, there is a dipole because they're separated. You have
Okay.
plus Q here, minus Q here, they're separated a little bit.
But I thought you just said that the dipole is created when there's a difference.
Suppose, meaning that if an electron is supposed to be uniform, right?
Yeah.
More of the minus sign get moved over here, this is more minus,
Yeah.
right? By conservation of charge, then this is more plus, right? A little bit, by a little bit, right? So
Yeah.
let's try it again, right? If your electron has a charge of E, right? Or suppose it's positron, has a positive charge E, right? It turns out there is a structure. It turns out there is slightly more positive here,
Mm-hmm.
right? By epsilon, by conservation of charge, right? Because charge is conserved, right? Then you have slightly more negative over here.
Mm-hmm.
These create a dipole, right?
Yeah.
Usually a dipole is written as a vector.
Okay, so it's not like magnitude of it, it's it's just difference in charge?
Yes. So by the fact that you have a distribution imbalance, it creates a dipole.
But in that case, it cancels out to be zero, or?
No, it's not, right? Because the dipole is defined as plus Q times L.
Oh, right.
Right,
Okay,
right,
yeah.
Yes. So in this case here, yeah, the total charge is still still E, right? But on this side you have E plus epsilon, and on that side you have, maybe E over 2 plus epsilon, and then you have E over 2 minus epsilon. Right?
Okay.
So you polarize the electrons say, somehow.
Do
And it turns out anyway, the answer is really small.
does the positive and the negative part of the dipole, do they have to have the same magnitude?
Yes, by definition.
So then how could you do that with the electron?
No. Yeah, I mean, say again. Yes, I'm
well-
saying that an electron is equal to this is all a very good question. Monopole plus dipole,
Oh,
right? Suppose, I mean, now we all believe classical E&M, simple quantum mechanics, electron is just monopole, right? But you always want to push the limit of science, right? But that's the purpose of science. You want to look deeper, more accurately, more precisely. Well, what if an electron carries a small dipole, right? So I thought I'd tell you guys about it because it's a good experiment being done here. I didn't want to confuse you. Right? Mathematically, at least in the exposition that we're talking about, a dipole is just that. Plus Q minus Q separated by N. Okay? I don't have much time left. I don't want to erase that board. So I want to go back to the dipole, but before I can do that, some other discussion. Recall that potential is given by minus ds, right? This is a definite integral. Okay? And as you now know enough from your study of thermodynamics, right? This is a state function. Right? Potential is a state function. Right? So, if I have a function f that's continuous and differentiable, right, then I can define the gradient of f, okay, to be equal to df dx, the x direction, plus df dy, y direction, df z, the z direction, okay? Regular result of, since I don't know how to draw in 3 dimension, in 2 dimension, was a function in d, right? X, y, the direction of f, say, right? And have some landscape like that. To make it simple, just make it into like something that looks more like a Gaussian. Right?
So it's
this is like a
3D, not 2D?
Yeah, this is 3D, right? But there's a function of only x and y. There is no z.
Oh.
Right? If there is a z, then I have to draw in 4D, right? So this is the x and the y is the 2 independent variable of space. And this is, this is f.
Oh.
Sorry. Okay?
Okay.
So it's like that, right? So let's pretend it looks like a Gaussian. Right? So these are line of constant height. Okay? Okay? And this gradient of f turns out to be a vector pointing in the direction of, this is very important, in the direction of steepest ascent. Okay, so if I want to calculate a differential df, an exact differential df, right? This is just equal to df dx times dx plus df y direction plus df z. This is partial, by the way, right? These are all partial, and this is exact differential. And I can rewrite this df to be a dot product of a gradient of f with ds, right? And ds is just a line integral in any direction you want. So this is df. It's going to be ds, right? Ds is dx, y, z. And you know from the dot product, this is just the magnitude of the gradient times ds times cosine theta. Right? So when cosine theta is 1, this is the highest, right? So when the direction of your path, if the direction of your path is along the gradient, then you get the highest the highest differential in F. This is what it means by the gradient of F is a vector that point in the direction of steepest ascent, right? You get the highest increase in grade by following along the gradient. Okay? Is it clear so far? If it's not clear, read the book. I want to give you some parts here. People are familiar with that from Math 53, right?
Yeah.
Okay.
Except at the time it didn't understand it now.
So let's substitute potential for that, right? Then I have V is equal to gradient of V divided into ds, right? Okay. But also, you know, from a definition of potential is defined as minus the integral of E ds, right? Some R, some indefinite integral, right? So then dV is just minus E ds. Okay. So comparing these two equations here, right? They're the same, right? Then you conclude that the electric field E is equal to minus the gradient of potential. Okay. So this is the differential form of basic, this equation and this equation are the same, right? This is the integral form, this is the differential form. Potential is a line integral of electric field times ds. The inverse of that is that electric field is just the gradient of potential with a minus sign, right? Okay? So, and the reason for the minus sign is that in this example here, you want to make sure that the kind of one, I mean, it's by definition, right? We put the minus sign here, just to conform with the definition of energy. You want the electric field to point, this is potential. Did I make a mistake somewhere? You want the electric field to point from high potential to low potential. You learned this from before, right? Like you want the electric field E to point from high potential to low potential. Okay. So in this case here, that's the reason for the minus sign. So it's here you want the electric field to point down. Okay. Since potential is given by minus sigma z over 2 epsilon naught, right? Then the electric field here is minus the gradient of V, but in this case here the gradient is only the derivative with respect to z, right? So it becomes minus dz of minus sigma z over 2 epsilon naught. Right? And minus cancel, dc is 1, so the electric field becomes sigma over 2 epsilon. Okay, is that clear? Okay. And notice that same here, right? This direction. This is the direction of a steepest descent because of the minus sign it becomes descent, right? This is your equipotential line. This is the everything in this plane have the same potential, and the electric field is normal to that plane, right? And this is the direction of the steepest descent. Okay. So this is another point. The gradient of f is always perpendicular to f equal constant. Right?